Hi there and welcome to this lecture segment on igneous rocks. In this lecture we're going to focus primarily on the identification of some of the most important primary igneous rocks on our planet. We're going to take a look at ones that form from lava flows. We're going to take a look at rocks that form in the magma chamber over millions of years. And we're going to take a look at a few of some of the special igneous rocks that we can get around a volcano. So let's go ahead and get started. Let's go ahead and take a look at the next slide. So igneous rocks are basically defined by their textures primarily. The textures give really important clues to the cooling history of that rock. And being that we're talking about igneous rocks, cooling is a big deal, and definitely in the formation of the rock itself. But more importantly, the speed of the cooling plays a big role in how the rock will look as well. The faster the rock cools, the smaller the crystals are going to be, and in some cases crystals won't form at all if the rock is cooled very, very quickly. And in the case of what we call glassy texture for igneous rocks, you'll see that down here at the bottom. We have this obsidian here, which is all glass. If you looked at this under hand lens or under a microscope, you wouldn't see any crystals in there at all. It's very smooth and basically lacks crystals because it cooled so fast, crystals didn't even have time to form in the chilling process. This rock here that's also glassy texture is also something that cooled very, very fast and is due to the fact that this particular lava also had a lot of air bubbles in it. And this is called pumice. It is very, very light. It's full of air holes. In fact, it's so light that it can float in water. So it's still glassy because it doesn't have any crystal structure within it, but what makes it look different from the obsidian is the fact that it's got a whole bunch of air bubbles in it. The top textures in this slide, phaneritic, aphanitic, and porphyritic, all have to do with the speed of cooling as well. The larger the crystals, the faster the rock or the slower the rock has cooled. The larger the crystals, the slower the rock has cooled. So granite, as shown in this particular sample, there's several different types of phaneritic igneous rocks. Granite is just one example. And you can see that it's peppered with light and dark crystals, and all of those crystals are fairly large. You can make them out with your naked eye at this scale pretty decently, and of course with a hand lens it would be super easy to make out each of these individual crystals in this particular sample. Whereas aphanitic means that you have very small crystals in the rock, and they're interlocking for both of these, for the granites, for the phaneritic textures and the aphanitic textures, including granite and basalt. The crystals are all interlocked as they cooled. This cools very quickly in comparison to granite. We've talked about the cooling speed of granite already. It takes literally millions of years to get crystal sizes this large in the magma chamber. Whereas for aphanitic texture, this can cool in the matter of hours, and you can get crystals growing. The obsidian pumice, we're talking literally seconds of before it's completely solid. So basalt takes a little longer. But in comparison to the granite, it's still very quick cooling. Now, porphyritic texture is a unique texture because it's got large and small crystals in it. And the reason why it has both is actually quite simple. The reason for the crystal size is still the same. Large crystals cool relatively quickly, large crystals cooled relatively slowly. And what's happened is, if you think of a volcano with its magma chamber underneath, that magma chamber is not just liquid. It's got crystals in it and it has gases in it as well. And so we've got all three phases of material, solid, liquid, and gas, in a magma chamber. Now, crystals are actually actively growing and getting bigger and bigger in the magma chamber over lots and lots of time. And they kind of float in the magma. If you have crystals floating in a magma and then the volcano erupts that liquid, those large crystals that are floating in the magma are going to go up with it. And so what happens is the large crystals come up with the magma, go up to the surface in the volcanic eruption, and then that material solidifies once it reaches the surface within a matter of hours. And what you end up getting is a texture that represents the crystals that took a long time to cool, the larger crystals, and then the crystals around it that are smaller that actually took only a few hours maybe to cool and solidify around it. So a porphyritic texture gives you a history of that rock that's actually really cool, because it basically shows, okay, you've got the crystals that have been growing a long time in the magma chamber, and then you've got these crystals around it that cooled real quick because of an eruption. So that's basically how you would interpret these textures. It's not actually that difficult to do, but these names are kind of unique and may have you may have take some time to have to remember the difference between these. They actually sound fairly similar to one another, so it could be a challenge to remember, but just do that, and the actual texture itself is actually not a big deal. I think it's pretty straightforward to understand once you get the names down properly. All right, let's go ahead and go to the next slide now. And one last texture I want to talk about, it's called pyroclastic texture. It's not due to solidifying lava at all. It actually has to do with pieces of mostly volcanic material that's been broken apart and ends up being welded together in what's called a pyroclastic flow. And this is an example of a pyroclastic flow right here, coming down the side of Mount Pinatubo in 1991 when it erupted then. But even though it doesn't look like it from this picture, it is very, very hot inside of that ash cloud, many hundreds of degrees Celsius. So it's really, really hot. And in fact, you might be wondering about this poor truck that's coming toward the photographer there. That's actually, the photo's coming from a helicopter that was there to rescue those people who are racing in that photo towards the helicopter. And that pyroclastic flow is moving very rapidly. You can't tell that in the photo, obviously. But of course, those people do not want to get caught up in that because you'd be killed instantly. But after all the dust has settled, literally, you end up finding these pyroclastic rocks left behind. Basically, pieces of volcanic and other material welded together due to the high heat of this cloud. All right, let's go ahead and go to the next slide. And Bowen's reaction series is a way in which we actually talk about the crystals and what point they actually crystallize at, the temperature in which a magma goes into a solid form. Much like water crystallizes into ice at 32 degrees Fahrenheit or 0 degrees Celsius, the lava and the magma have their own crystallization temperatures as well. It's a little more complicated, slightly more complicated than the water crystallizing in the ice at one particular temperature. But the idea is about the same. And are we going to delve into any details regarding that in this class? No. If you were to major and take a volcanology class or a class on igneous petrology or something like that, then you would delve into those details. But for now, we're just going to talk about the lava solidifying into these mineral assemblages to produce these igneous rocks. So you'll notice that the Bowen's reaction series over here shows the temperature regime for where these minerals will crystallize out. So the highest temperatures you can follow along the diagram along that stretch, and you would come up with those particular rocks. And then at more moderate temperatures, you would have these mineral assemblages creating mafic, and then you're getting cooler again, getting more into intermediate mineral assemblages, And then the lowest temperature, basically the last minerals to crystallize before everything becomes solid, is going to be more felsic and be made up of these mineral assemblages. So what we're going to go do now is talk about each of these rock types and their mineral assemblages without looking at this actual table, just talking about it qualitatively speaking. So let's go ahead and go to the next slide and take a look at the ultramafic rocks. So basically, for ultramafic rocks, there are two types. There is peridotite and there's comatite. Now I'm going to go through the ultramafic rocks, then the mafic rocks, then the intermediate rocks, and then the felsic rocks. And in each of those slides, I am going to list the first name. The first rock name is going to be what we call the intrusive igneous rock. The intrusive igneous rock is the rock that's going to be made up of the large crystals, because you already know this, because it took a long time to crystallize. It crystallized basically at depth. And then the second igneous rock name that's going to be mentioned is going to be the rock that crystallized very quickly at the surface of the earth. So for ultramafic rocks, we have two types, peridotite and comatite. And it's unique because today ultramafic rocks only occur in the mantle. But that's not true of all of Earth's history. Earth used to be a very hot place throughout, from the top to the interior. Right when it formed, it was very, very hot. And in Earth's early history, as the Earth was solidifying into the rocky planet it is today, it's believed that comatite formed at the surface of the planet. So comatite today is actually a very rare rock to find. It's basically ultramafic rock that's made of very tiny crystals. This is a picture of it here, but the crystals look large to the eye, but this is actually a microscopic view. So it's like you're looking in a microscope at the crystals. So it's not as large as it may appear in the picture. And there's only a few places in the world that you can find comatite outcrops, and that's mostly in Africa. We don't even have any outcrops like that in the United States. Peridotite you can find much more commonly, mostly embedded in basalt that's come up from the mantle, usually through decompression melting processes. It brings the basalt up and brings chunks of peridotite with it. And so the peridotite didn't crystallize at the surface. It was crystallized at depth in the mantle, but then got brought up and in a solid state up to the surface. So that's where we usually see peridotite. And it's like that today in the mantle. So regardless of whether you're talking about peridotite or comatite, the mineral composition is always olivine with maybe a slight amount of pyroxene in it. Some things you need to think about is that it's got the highest amount of iron of all of the rocks. We've talked about that already with Earth's composition. And if you're in Geology 100 in the minerals section of the course. And also because it's very hot, it crystallizes at very, very hot temperatures. Well before that magma can make it to the surface, it's already crystallized at depth. And today the mantle is just made of that at depth without much liquid down there. The magma is going to obviously have a very low viscosity. Remember, viscosity is the resistance to flow. So if you've got a low viscosity, that means you have a low resistance to flow, which equates to a very fluid material as a liquid. All right, so let's go ahead now and go to the next slide and talk about the mafic rocks. So mafic rocks are called gabbro and basalt, gabbro being the large crystal variety and basalt being the small crystal variety. And, basically here's what gabbro looks like, here's what basalt looks like. They're very dark colored rocks, and these have larger crystals than the very tiny crystals that you see in this aphanitic texture here. The mineral assemblage is pyroxene, plagioclase feldspar, and sometimes, but rarely, hornblende in it. Those are the three mineral types you find in these rocks. The magma is going to be very hot as well, and it's going to be cooler than the ultramafic magma if there was any in existence today, but it's going to be warmer than the other two rock types we're going to talk about here in just a moment. So generally the magma is going to have a very low viscosity in comparison to the next two we're going to talk about. It's a very fluid, runny magma, and we typically see those kind of eruptions in Hawaii. If you've seen images of Hawaiian eruptions like Kilauea, you'll see the lava flows very runny-like, and that's because of the low viscosity. This type of rock is found virtually everywhere. Because of its low viscosity and its very buoyant nature, it can actually penetrate a lot of different cracks very easily. Because of its fluid nature, it's also very hot, so it's very buoyant. It rises to the surface most readily because of its warm, buoyant nature. So it's something that we see in a lot of different volcanic environments. I've listed them in this slide. Mid-ocean ridge volcanism. So the ocean floor is entirely made out of mafic rocks completely. Hotspot volcanism, both oceanic and continental hotspots, you'll find mafic rocks in both environments. And then subduction zone volcanism. So the volcano types we're going to be talking about in this module, the composite volcano, stratovolcano, will produce mafic rocks as well as intermediate and felsic. A lot of people, when they are get tested on this, they'll just say, oh, it's just felsic. That is not true. It's mafic, intermediate, and felsic rocks that form those volcanoes. So we'll talk about that more a little bit later. Let's go to the next slide. So intermediate rocks are called diorite, that's the large crystal variety, and andesite, the small crystal variety. And it is basically going to be lighter in color than the mafic rocks, but still darker in color than the felsic rocks. And its composition is hornblende, plagioclase feldspar, and biotite mica. And the magma has now got a higher viscosity, meaning the magma has a higher resistance to flow than the mafic variety. So it's, basically a lot of people refer to that as thickened up a bit from the mafic variety lavas. They crystallize from a cooler magma, and that accounts for the higher viscosity of the material, along with the composition as well. This type of rock is only found in subduction zone volcanism, at least for the most part. I shouldn't say only. There's probably some unique exceptions to that, but almost exclusively it's subduction zone volcanism that produces this composition. Let's go ahead now and go to the next slide. Oops. That is the exception, actually. Continental hotspot volcanism is the exception. I was going to kind of not mention that, but and the reason why I was going to not mention that is it actually is quite rare to find it in places like Yellowstone and stuff. Usually those places are really felsic, but there are some exceptions, and so that this would be properly stated for a very rare occurrence in those environments. All right, let's go ahead and go to the next slide and talk about the felsic and silicic, or felsic/silicic type rocks. So granite and rhyolite are the two. Granite's the large crystal variety, rhyolite's the small crystal variety. Oops. Keep doing that, sorry about that. Granite is, and granite and rhyolite are both very light colored. They can be pink or peach in color. That's a lighter colored material that's coming from the potassium feldspar. Potassium tends to lend to a pink color in the rock a lot of times. And there's also quartz and muscovite and biotite, mica, and hornblende in these particular types of rocks. It's crystallizing from the coldest magma, so it has a very hard time squeezing to the surface. In fact, it's got the highest viscosity as well because of the cold nature of the magma, but also because of its chemical composition. Viscosity is affected by both composition and temperature, and we'll talk about that more in a separate lecture segment for this. But these rocks are found again, exclusively in subduction zone volcanism, and definitely found in continental hotspot volcanism as well. This kind of rock kind of acts like a cap. It does make it to the surface. It's a very tough rock and tends to act as a cap to basically allow pressure to build up inside the volcano. So when that pressure basically exceeds the strength of this particular rock type, it'll actually cause this rock to explode and then have a violent volcanic eruption as a result of that. So the chemical composition of this, the nature of this kind of rock is actually strong and actually allows for these subduction zone volcanoes to be as explosive as they are, as well as the continental hotspot volcanism. Again, in a future segment for this module, we'll talk about that in a bit more detail. All right, so for other igneous rocks, there's a few others I wanted to go through with you. These up here. So basically, tuff is that pyroclastic rock I introduced you to earlier as a texture. Texture is pyroclastic. It's not made, it's the only rock that we've talked about that's not made from a lava flow. It's welded pieces of rock that get welded together in that pyroclastic ash cloud, because that ash cloud is really, really hot. And it's so violent that it's breaking pieces of rock up. And so what you end up with is a rock with welded together angular fragments. It's very unique looking in comparison to a crystallized rock that's crystallized from lava or magma at depth. And obsidian / pumice, that's the quick cooled magma that doesn't cause any crystals at all because it cooled so fast, crystals had no time to grow. Pumice is very what we call vesicular in nature. Vesicular means air holes throughout. And pumice is that kind of rock. Obsidian doesn't typically have any air holes. It doesn't at all, actually. It's very glassy and smooth like you see in the photo there. All right, so that is the end of this lecture on igneous rocks. I will see you in the next one. Thank you very much.